Welcome, Year 11, to the wonderful world of stoichiometry. Today we're going to be looking at chemical equations and the mole, and particularly at this idea of stoichiometry, which is the calculation of quantities of materials consumed and produced in chemicals reactions. So today we want to be able to use this law of conservation of mass to relate that to the mole concept. Moles, the molar mass. We're going to use an appropriate stoichiometric ratio to determine that reactants can be limiting. We're going to appreciate that experimental yield can be different from theoretical yield. Then we're going to use mathematical representations to do a whole lot of things. So we're going to think particularly of these molar masses, and we're going to then be looking at the calculating the amount of reactant produced in a substance, for example, and then we're going to look at the experimental yield from given data. So first of all, the law of conservation of mass is what matter cannot be created nor destroyed. So that means in ordinary chemical reactions, the total mass of reacting substances is equal to the total mass of the products. So that means all atoms in the reactant side of the equation must appear on the product side and in equal numbers. No new elements can appear, and no elements can disappear in this. So when we look at a chemical equation, there are some important symbols. So there's S, L, G, and AQ. They are our states of matter. So S for solid, L for liquid, G for gas. AQ is dissolved into water. Remember, aquaman comes from the water, so aqua is aqueous solution. We then have an arrow, which means yields, and that's a reaction going forwards. And then we have a plus sign, which symbolizes that there are two separate reactants or two other products, for example. Then there's a two-way arrow, and that's used in place of a one-way arrow for reactions that can also go backwards. And then we've got symbols on top of the arrows, such as heat, or a little triangle, which is delta, which means energy or heat energy is supplied. And then we can also write the names of catalysts above arrows. For example, in this case, it's the manganese dioxide catalyst. When we balance equations, there's going to be a few main steps we want to look at. First of all, we want to find correct formulas for all the reactants and products. Then we'll write a skeleton of the equation. So we're going to place the formulas for the reactants on the left and the formulas for the products on the right. And they're going to be separated by a yield sign. And if there's more than one reactant or product, we're going to have to separate them by a plus sign. We'll determine the number of atoms on each element in the reactants and products. And remember that polyatomic ions can work as a single unit and will appear on both sides of the equations unchanged. So remember, we've talked about a few polyatomic ions. So for example, nitrate or sulfate, you can treat them as a group. Now, step 4, balance the elements on one side at a time using coefficients, and then when no coefficient is written, assume it is just 1. So start by balancing elements that appear only once on each side of the equation. Now remember, you cannot change the subscripts, because then you would change the formulas of that reactant or product. So that would be inventing a new substance. And then we'll check the numbers of each type of atom on each side to make sure that they are equal. So you may want to do a table like this. And then we'll make sure that all the coefficients are in the lowest possible ratio. So we're simplifying it. And add in other symbols such as state, so solid, liquid, gas, or dissolved into aqueous solution if they aren't known. So we know that in chemistry we are looking at changes, and matter can change form, and we've had a little look at this slide before, and we said, well, a physical change is a change in those three S's: the shape, the size, or the state of the substance. But when we're looking at chemical reactions, there are three main groups of reactions I want to discuss with you first of all. The first one is synthesis, when you add two simple substances. So you might add two elements and you'll come up with a compound. The next one might be decomposition then. So when we're going from something more complex into something simple. And then we've got displacement, and that's when partners are being swapped. So the cations and anions swap places. So I'd like you to have a little practice at these. So pause your video and give these a crack. I'll do a few and hopefully we won't spend too much time on them. So if I'm looking at this, I'm giving you the skeleton equations, and so therefore you can assume that all the formulas are correct and you've got here. So you just really need to look at the coefficients and change. So I'm looking here, I can see a 2, and I can only see one on here. So if I look there, I can see that I've got 2 hydrogen atoms on the left and the right. Now, if I look here, I've got 8 sulfur and I've got 1 sulfur. So if I put an 8 in front of that, that's fine, but now I have to change my silver, which is Ag, and 8 times 2 is 16. So that looks good there. And you can recognize these as what? Synthesis reactions. And the next one is we've got a chrome, and what do we got? We've got 2 chrome over here and we've got 3 here. So we've got a problem, because if I put a 3 here, well, that's 3 times O2, that's 6, isn't it? So what do we do? We'll put a 2 in front of that. So we do have 6 now. We can go 3 there, so that's fine. So we've got 6 oxygen on the left and 6 oxygen on the right, and we'll put in 4 there because we've got 2 times 2 is 4. Now we've got potassium chlorate producing potassium chloride and oxygen. Likewise, we've got an O3 on this side and an O2 on that side, and you can see this is a decomposition reaction now. So what did we say? We put a 3 there and a 2 there, and that should just balance up nicely to be 2 there. So if I'm counting my atoms on my left and the right hand side, I can see 2 Ks, which are potassium, I can see 2 Cls, which are the chlorines, and then I can see 2 times 3 on the left, which is 6 oxygen, and 3 times 2 on the right, so that's 6 oxygen. And then we've got our sulfuric acid, which is H2SO4. I'm counting on the left, I've got 2 hydrogens. I'm counting on the right, I've got 2 hydrogens. This looks balanced already. And look at the sulfur, there's only 1 sulfur on the left and there's 1 sulfur on the right. There are 3 oxygens there and 1 oxygen there, so that's 4, and I can see 4 oxygen there, so that's balanced. You can leave that as is. Next one is hydrogen carbonate is decomposing into water, so likewise it's balanced already, isn't it? I can see 2 hydrogens on either side, I can see 1 carbon on either side, and I can see 3 oxygens on either side, so that's all very nice. So if you are in an exam situation, just to idiot proof it, you may want to just point out to the teacher the bleeding obvious that you can put in a 1 there, and you know that that's the right formula. Okay, now let's have a look at this one. This looks more like a displacement reaction, doesn't it? And it looks like a single displacement reaction because we've got an element plus a compound giving a compound plus an element. So first of all, let's have a look. We've got 2 hydrogen there, and I might just go a 2 over there. That looks good. Now this is our polyatomic ion group called nitrate. So remember, nitrate was NO3 minus. Now I've got 2 of those nitrates. Now I've got 2 of those nitrates there. So I'm good for nitrate. I'm good for hydrogen, and I'm good for magnesium. So that equation is now balanced. Now let's look at zinc. We've got zinc and sulfuric acid. We'll make zinc sulfate and hydrogen. I can see 1 zinc on the left and 1 zinc on the right, so that's fine. Then I've got one hydrogen molecule, so that's 2 hydrogen atoms on the right and on the left, so that's good. And then one sulfate group. Remember, that's the other polyatomic ion that we'll work a lot with, so that's nice and balanced. And you may want to idiot proof that for your teacher. Now we've got aluminium sulfate and calcium hydroxide producing aluminium hydroxide and calcium sulfate. And this is going to be a little bit trickier, so let's have a look here. I've got 3 sulfates on the left hand side, so if I put a 3 in front of that, let's see what happens. And means I'm going to have a 3 in front of that, and then I may need a 2 in front of that, and that looks like it should be balanced. The next one is silver nitrate plus potassium phosphate, so we will make silver phosphate and potassium nitrate. So let's have a look. I've got a 3 potassium on the left, I'll need a 3 potassium on the right. Now I've got how many silvers on the left? I've got 1, but I've got 3 silvers on the right, so I'll have to put the 3 there. And let's have a look. I've got 3 silvers on the left and 3 nitrates on the left. So I've got 3 nitrates and 3 potassiums. That's good, and that's all good. So that's 1 there, that's 1 there. Okay, the last one is copper bromide and aluminium chloride will produce copper chloride and aluminium bromide. So this looks like a 2:3 ratio thing, doesn't it? So let's have a look first of all at my chloride. So if I've got aluminium chloride, I can see a Cl3 on the left hand side. So if I go a 2 of them and a 3 of them, and a 2 of them and a 3 of them, it should balance out nicely, hopefully. Now we're going to look at calculating mass to mass. So what we're using here is stoichiometry, and we're trying to predict the amount of mass in, for example, another reactant or a product. So you may want to use stoichiometry, for example, if you're in industry, to say, oh, I've got reactant A, how much reactant B will I need to produce a product? Or if I've got these 2 reactants, how much product will I produce? In this case, it's in mass. So for example, mass of reactant A to the mass of a product. And there are going to be 5 steps here. So first of all, we want to balance the equation. So hence a go at what we've just been doing. Then we're going to convert the mass to moles, and so remember our number of moles equals the mass in grams over the molar mass, which is grams per mole, and you read that off the periodic table. Now we're going to set up mole ratios, so we're just looking at the ratio of one reactant to the product or one reactant to the other reactant. And then we'll use those mole ratios to calculate the number of the desired substance, and then we'll convert those moles back to mass. So if we have a look at an example, this will take a few slides. So we're reacting aluminium with oxygen here. So if we've got 6.5 grams of aluminium reacting with an excess of oxygen, that just means we're probably getting oxygen out of the air, and we've got unlimited amounts. And you can see this picture down in the bottom right hand corner. Aluminium powder will combust quite well. So if we want to set up our equation, first of all, we want to identify the reactants, and we're going to write the balanced equation. And remember that every reaction needs a yield sign, so that's that arrow. Then let's consider the reactants. Well, that's got to be aluminium, and it's got to be oxygen. The products, well, we can figure that out. It's going to be aluminium oxide. And so let's have a look at the balance coefficients. So there's a problem here that oxygen hangs around in molecules in the air, doesn't it? So it's O2 in the air, and over here it's O3. So what we're going to need to do is just do the 2 and the 3 relationship there that you'll see pop up a fair bit. So we now know that 4 moles of aluminium and 3 moles of oxygen will produce 2 moles of aluminium oxide. So we're going to now look through the mole ratios. So for example, we'll know that we've got 4 moles of aluminium. We'll produce 2 moles of aluminium oxide, so that's a mole ratio of 4/2. Or 4 moles of aluminium to 3 moles of oxygen being used. If oxygen was a limiting factor, then that's a reactant A compared to reactant B, and that's a 4:3 ratio. So there was a little issue there, sorry folks. So let's continue with this problem. So we said that 4 moles of aluminium and 3 moles of oxygen will produce 2 moles of aluminium oxide. So we've now balanced the equation. So we want to now convert mass to moles. So we use our formula, N equals M/M, so the mass in grams over the molar mass. And we can read off the periodic table that aluminium is 26.98 grams per mole. So let's convert that now to moles. So it's just 6.5 grams over 26.98 grams per mole. And that will give you 0.241 moles. Then we're going to consider our mole ratio. So we've got 2 moles of aluminium oxide for 4 moles of aluminium. So that means for every 2, we're just going to get half this number, because 2/4 is a half, isn't it? So 2/4. So multiply it by 2/4 to get 0.1205 moles of aluminium oxide. And then we just want to use our formula, N equals M/M. We just need to rearrange that to say our molar mass times the number of moles should be the mass in grams, and that's 12.3 grams. Now we can also notice NASA, for example, use this relationship when they combust hydrogen and oxygen and they produce gaseous water. And this is a very vigorous flame, and it's a hydrogen fuel cell. So what I'd like you to consider now is how many tons of hydrogen a space shuttle needed to carry for each ton of oxygen. So what we want to do is balance the equation, convert the moles, mass to moles, set up the mole ratios, use those mole ratios to calculate the moles of the desired substance, and convert moles to mass. So we know that 2 moles of hydrogen plus 1 mole of oxygen should produce 2 moles of water, and that's gas. So we've got a mole ratio of what? 2 moles of hydrogen to 2 moles of water. So we also have 1 mole of oxygen, to 2 moles of water there. So we've got 1 million grams, that's a ton of oxygen. And oxygen weighs 32 grams per mole. And so let's now convert that to moles. We've got a million grams divided by 32 grams per mole. Now that gives us what? 3.125 times 10 to the power of 5 moles of oxygen. And let's now convert that through the mole ratio. So for every mole of oxygen, 2 moles of H2 are required. So we're going to need double that. So that's going to be 6.25 times 10 to the power of 5 moles of hydrogen. And then we just need to multiply that 6.25 times 10 to the power of 5 times that 1.01 grams per mole. But we know that, hydrogen is a H2 gas. So the hydrogen atom has what? 1.01 grams per mole. But so that's just H, but H2 has got to be double that because hydrogen gas. So we're going to go 6.25 to 10 to the power of 5 times 2 grams per mole should give you 1.25 times 10 to the power of 6 grams. So it's a bit over a ton of hydrogen being stored there. So let's do one final example. So 2 grams of iron is reacted with 8 grams of copper sulfate pentahydrate. Now how many grams of copper will be produced? Now copper sulfate pentahydrate has penta, so 5 water molecules attached to it. So when you weigh out the copper sulfate crystals, you're going to have to account for those 5 water molecules attached to it. When they get dissolved into water, they'll disappear, of course. So we've got copper sulfate pentahydrate plus iron to produce iron sulfate and copper. Now this all looks like a 1 to 1 to 1 to 1 mole ratio, but let's calculate the number of moles of copper sulfate pentahydrate. So we've got 8 grams, which is our mass. Now this is a molar mass. You'd have to add up each of these. So 1 copper, 1 sulfur, 9 oxygen and 10 hydrogen there to get that 249.72 grams per mole. Now 8 grams divided by 249.72 is 0.32 moles. So in theory, we will produce, for every 1 mole of copper sulfate pentahydrate, we produce 1 mole of copper. So if we've got 0.32 moles of copper sulfate pentahydrate, we'll produce 0.32 moles of copper. Now let's just run through our moles of iron as well. So we've got 2 grams of iron. And so we want to calculate the mole ratio, the moles of that first. So number of moles equals the 2 grams divided by iron's molar mass, which is 55.83 grams per mole. And so that's 0.035 moles. Now, I can only use what the smallest amount is. So I'm going to have a little bit left over here, and I'll talk about that soon in the next slide. So we're only going to be able to produce 0.032 moles of copper because this is the smallest one. We'll have a little bit left over of iron in this case. So 0.032 moles times 63.55 grams per mole should predict to get about 2.03 grams. So a limiting reagent, as you saw there, is any reactant that is used up first in the chemical reaction. So it determines the amount of product that can be formed in a reaction. So if we have a look, if we're making up a bunch of sandwiches, and each sandwich is to have 2 slices of bread, 3 bits of meat and a slice of cheese, and you have 6 slices of bread and 12 pieces of meat and 5 slices of cheese, you're going to make enough for 3 sandwiches, but you're going to have excess amounts of cheese and meat in this case. So the bread is going to be the limiting factor. Now you can see this down below in these 3 pictures too. The middle one here has a complete combustion, so that's a good combustion, where you might have insufficient oxygen or propane in the bottom bottles there. So let's put this into practice. If 15 grams of copper 2 chloride react with 15 grams of sodium nitrate, how much sodium chloride can be formed? So we're going to look at reagent 1, so the mass of copper chloride, and we're going to go to the moles of copper chloride, predict the moles of sodium chloride to determine the mass of sodium chloride. So the number of moles in copper chloride, well, we've got 15 grams and it's 134.45 grams per mole. So that will give us 0.11 moles of copper chloride. But if I look at my balanced equation, I need, I'm going to produce, for every 1 mole of copper chloride, I'm going to produce 2 moles of sodium chloride. And that's, you can quickly see that that's got a Cl2 there, and that's got a Cl. So I've got twice as much chlorine on the left-hand side as the right-hand side. So to determine the mass now, we've got mass equals the number of moles times the molar mass. So 0.22 moles of sodium chloride times 58.44 grams per mole for sodium chloride. And that will give you 12.97 grams. Now if we look at sodium nitrate, we've got a mass of 20 grams of sodium nitrate, but we need 2 moles of that. And that will then produce 2 moles of sodium nitrate. So we need 2 moles of sodium nitrate to form 1 mole of sodium chloride. So in this case, it's the mass of sodium nitrate is 15 grams, and the molar mass of sodium nitrate is 85 grams per mole. So that will give us 0.176 moles of sodium nitrate, and that should therefore, it's 1 to 1 because it's just 1 sodium to 1 sodium, should give you 1.76 moles of sodium chloride. that should be able to produce 10.23 grams of sodium chloride. So this one here is smaller. That means that's going to be our limiting reagent because it produces less sodium chloride. In reality, we never get 100% of what we expect. So we now think about the percent yield. So how efficient is your chemical reaction going to be? And that's described by the percent yield. So the theoretical yield is what we work out through stoichiometry. The actual yield is what you measure in the lab when you do it. So we've got calcium carbonate. It's being decomposed by heating, and it's shown in the following equation. Calcium carbonate is heated, so that's the yield sign with the delta above it, and it decomposes to form calcium oxide and carbon dioxide. So what is the theoretical yield if 28.4 grams of calcium carbonate is heated? And then what is the percentage yield if 13.1 grams of calcium oxide is produced? So our strategy is going to be the mass of the calcium carbonate to the moles of the calcium carbonate to the moles of calcium oxide to the mass of calcium oxide. So let's do that. The theoretical yield is the number of moles. So that should be the mass over the molar mass. So that's 0.024 moles of calcium carbonate. So that should give us 0.24 moles of calcium oxide, and we'll multiply that by its molar mass. So in theory, we should get 13.9 grams. In here, we've said we've got 13.1 grams there. So all we need to do is do the 13.1 divided by 13.9. We multiply by 100%, and to get a percent yield of 94.2. That was a big one, I'm sorry folks. So can you consider the conservation of mass? How are you with this stoichiometric stoichiometric I should say, that's our mole ratios. Can you appreciate the difference between experimental yield and calculate the percentage yield using the appropriate mathematical representations? When you're happy with that, please have a go at these questions in your textbook.